Okay, here we are with the third chapter of this course on dynamics of the tropical atmosphere and oceans. Here we look at some fundamental processes. We will see what we mean by that. Essentially, we look at the atmosphere and see how the tropical dynamic understanding evolved, starting with a slightly wrong assumption by, let's say, Jules Charny in the 1930s and 40s about the scale of tropical motions, which tries to explain how you can actually generate the circulation in the tropical atmosphere if it's non-divergent. We'll see what that means. As we already mentioned in the previous chapter, the tropical atmosphere is essentially barotropic because of convection mixing things in the vertical, but that doesn't explain where the convection came from in the first place. So there are various issues to be resolved there. And then we look at the ocean, which is a bit simpler in the sense once you have atmospheric heat fluxes and winds, we will just look at wind-driven circulation here. You can explain the frictional forcing of the ocean surface by the winds and the Ekman circulation that generates, and the communication with the interior that is generated by this wind forcing. And look at a little bit at how the interior ocean adjusts to this forcing from the Ekman layer or the boundary layer. So that's the big difference between the atmosphere and the ocean. Atmosphere is heated from below by the ocean, and in the middle by the radiation and latent heat release. So it's the fundamental processes are basically looking at these few issues. There are a bunch of non-dimensional numbers we'll have to consider. Ratios of forces, rotational, inertial, frictional, etc. And they allow us to compare models to observations and observations to lab experiments. Imagine doing large-scale atmospheric processes in a little lab water tank or wind tunnel. The comparison is made easier if you have non-dimensional numbers that allow you to compare the processes. So let's start with this idea of baroclinicity. We said tropical atmosphere is mostly barotropic. What do we mean by baroclinicity? Essentially, when the density is a function of pressure and temperature, as it is in the atmosphere, then the vectors grad rho and grad p are not orthogonal to each other. Then you get a baroclinic atmosphere as in the mid-latitudes, which essentially allows non-divergent flows, communication between the lower and upper levels, storage of potential energy, and various processes by which potential energy can be converted into kinetic energy. So the question then is, how is potential energy converted to kinetic energy in the tropics if the atmosphere is mostly barotropic? We can look at this very easily. You look at the density as a function of pressure or height. As a zonal mean meridional section, that is our favorite. And you can see that in the tropics, the grad rho and grad p vectors are essentially parallel to each other. That is our essential definition of barotropic system. And as you go off the tropics into mid-latitudes, you begin to have the grad p and grad rho intersecting with each other. And the winter hemisphere will have a greater angle between grad p and grad rho because the equator to pole temperature, baroclinicity, and so on increase. But you can get a sense of the stored potential energy here. In a simple sense, you can see that there is heavier air at the surface here than in the tropics. Then why doesn't this heavier air just rush down to the low latitudes and lift up the lighter air? Obviously, we are balancing the rotational effects with the stratification that is maintained by these processes of heating and cooling. So this locked up potential energy then, because of rotation, you can maintain these density gradients against gravity, let's say. That's what gives us the potential energy that's locked up, and there are processes which release it into kinetic energy, which is our weather and climate. Let's start with the simplest expression we had of the potential temperature, which is by definition just the temperature a parcel of air would accomplish or reach when it's moved adiabatically to a reference pressure, let's say at the surface. So it's the in situ temperature times PS, the standard pressure, divided by P, its in situ pressure where it starts, to the power of R over Cp, where this is the ideal gas constant and Cp is the heat capacity at constant pressure. When the air parcel has water vapor in it, you have the equivalent potential temperature, which is a function of the dry potential temperature and is related to the latent heat of condensation evaporation, vapor pressure at saturation at that given temperature. Essentially, that means if the parcel equivalent potential temperature is needed, then we raise it to a place where all the water vapor is condensed, releases latent heat, achieves certain temperature at that pressure. Then we move it down again to the reference pressure. Obviously, because of presence of water vapor and the release of heat, you would expect equivalent potential temperature to be warmer than the potential temperature, the dry air parcel. You can look at that in terms of, again, the zonal mean meridional sections for June, July, August, and December, January, February. At any given latitude, as you go up in the atmosphere, the potential temperature increases, and we again see this near barotropic structure in the deep tropics. Obviously, this means that the atmosphere is stable to dry convection. If you move a dry parcel of air adiabatically, then its buoyancy changes in such a way that it tends to come back to its original position. So it's basically statically stable. You see the flatter structure here. You see this sloping upwards towards high latitudes in both seasons, but there are obviously differences. In the boreal summer, you have warmer temperatures, the ITCZ moving to the north. Even though we're talking about potential temperature, this is from the real world, so it has the impact of humidity in it. And you can see the difference from the summer season to the winter season, especially in terms of the colder 290 Kelvin isentrope, for example, coming further down here from about 40-50 north to 30 north or so. Okay, so those kind of subtle things have to be watched out for. These are called isentropes because if you move an air parcel along it, entropy doesn't change. The subtle difference with the equivalent potential temperature is seen here. It's 310, about 300 here, whereas it's 330, and you can see that there is a negative gradient approximately here, which refers to the which corresponds to the instability which allows convection to happen. So the structure is determined by the fact that there is convection. So we'll see that the equivalent potential temperature shows that instability which is satisfied by convective activity, but it's kind of a chicken and egg argument about how convection is driven in the first place. Okay, so just remember these kinds of subtle differences, but remember the physics, because the equations are there always in the book, but finding the science behind it, understanding the physics behind it is important, because as soon as you see the equation, you should be completely comfortable in explaining what the equation actually represents, what approximations may have gone into it, and what the consequences of the approximations are in terms of the balances, dominant terms, or the required conditions to meet the approximations in the first place, and so on. Okay.